The following content is created by Dr. Avitek. Your support and donation will help me continue to offer high-quality educational resources for free. To make a donation, send an email to 6drcyril@gmail.com or comment donations below.
Welcome back, guys. In this video, we're going to be finding the Laplace transform of t to the power of n. Now, there's actually a very tedious way of doing this, and there's actually a very simpler way of doing it. It all depends. Now, let me do the hard one, or what I consider the hard one. So what we're looking for here is the Laplace transform of t to the power of n. That's what we're looking for. Laplace transform of t to the power of n. That is what we're looking for. So in this case, this will be the integral from 0 to infinity, t to the n, e to negative st dt, because our function is t to the power of n. Okay, now what I'm going to be doing is I'm going to take integration by parts. Like I said, that's going to be a lot, but let's get started. Hold on, let me see. There's something I would have loved to do. Yep, okay, towards the end, I'll do it, and then for now, let me just use integration by parts. Now, you want to pick your, integration by parts. So let me just write it here. U dv is equal uv, take away integral of v du. All right, so you want to pick your u to be something that can differentiate and also reduce. So this is it. T to the power of n has to be u. T to the power of n has to be u. Because if t to the power of n is u, depending on what n is, if you differentiate multiple times, you should get 1 at some point. So you should get 1 at some point. Imagine if it's t to the power of 4. When you differentiate the first time, you get t cubed. Differentiate again, t squared. So it keeps going down. So that's what I'm going to be doing. So in this case, I'm going to say u is equal t to the n. Then dv is equal e to negative st dt. So now let's find the u. So when you differentiate to here, this will become nt to the power of n minus 1 dt. When you differentiate this u with respect to t, remember that there's a 1 here. So 1 times n is n, and then you reduce the n by 1. Now to get the value of v here, this is a derivative already. So for you to get back v, you need to integrate. So to integrate, this will become e to negative st divided by minus s, because you must divide by the derivative of this power, minus st. So now let's say the Laplace transform of t to the n will then become uv. It says we're going to have uv. So that will become t to the n e to negative st over minus s, because uv means these two things will multiply. So you have tn e to negative st over minus x, and then minus the integral from 0 to infinity of v du. So we now have where's v and then du. So these two guys will then multiply. So I think let me put this one first. So this will be n tn minus 1, then e to negative st over minus s dt. Now please take note, this expression here we still take our limit 0 to infinity. So our limit will exist everywhere in that expression. So it's still going to take our limit. Now let's bring out some constants. This will become t to the n. Oh, the t has infinity, so that's not going to be a constant. So only the minus s is a constant. So this will be minus 1 over s into t to the n e to negative st from 0 to infinity. And then here, n is a constant, the minus s is also a constant, so they'll both come outside. They'll both come outside. So this will become plus n over s integral from 0 to infinity of Tn minus 1 e to negative st dt. So this is what we have. This is what we have. Okay. Let's put in our limits for this very one. This will be minus 1 over s. Then we're going to be having, for this one, let's put in our infinity here. So this will become infinity to the power of n, then e to negative infinity minus 0 to the power of n. So the second time we're going to be plugging in 0, and then e to the 0. Then plus n over s. Now, if you notice for this case, we're just going to leave it like this. We're just going to leave it like this. So for now, let's say this is I n minus 1. Why is it I n minus 1? If you compare these two expressions together, what do you notice? You notice they are similar. The only difference is our n is now n minus 1. So if this integral was equal to in previously, that means this one here is equal in minus 1. That's what this one is going to be, in minus 1. So let's continue. Now this is minus 1 over s. Now in this case, take note, e to negative infinity is 0. So 0 times anything will be 0. Minus this is 0. 0 times anything is still 0. So this is plus n over s. Then we have in minus 1. So finally, everything here just becomes 0. Because 0 times this will just give me 0. So that's n over s. Then in minus 1. So that's what we have. Now this very expression, let's also find the integral again. So we'll keep on finding the integral, but we're going to stop at some point. That's why I said this is a little bit tedious. So we're going to find in minus 1 again. But remember that this is what in minus 1 is, right? This is what in minus 1 is. So we're going to be having I to the n minus 1 is equal integral from 0 to infinity. So we have in equal to this. So t to n minus 1 e to negative st dt. Now, we're going to repeat the same process. So u is equal t to the n minus 1. So this means that du is equal n minus 1 t to the n minus 2, because this is n minus 1. If you remove 1 from it again, that means it's a minus 2. And then dt. Then dv is e to negative st dt. So when you find v, this will be e to negative st divided by minus s. Okay, that's a whole lot. So let's proceed. Now I'm going to be putting these values into this expression using this formula. So uv would go first. So we have uv. So for uv, this will be t to the n minus 1 divided by, okay, let me also put the v, e to minus st, everything will be over s. And then minus the integral from 0 to infinity of v du. So that's these two guys at the bottom, v du. Well, let me write my du first. So that's n minus 1, t to the n minus 2, then v is e to negative st, then I put my dt, all over minus s. All right, now remember that this side must still follow our limit. It's in the whole expression, so you must follow the limit. Now, quick one. I don't want to stress myself. This will still give me 0. Remember, just from here, every single thing you see here, this is a similar one. It's a similar one, so it's still going to just be 0. Let's not stress ourselves. Now, this minus will come out to meet this very minus sign because it's a constant. The n minus 1 is also a constant. So this will be n minus 1 over s. Remember, minus times minus is plus. So this is positive. This is 0, so just straight away it's 0. So let it just go. Minus is plus. So this is n minus 1 over s. Then what's remaining is the integral from 0 to infinity. What's left here is t to the n minus 2, e to minus st dt. All right. Now, if you take a look at this again, this will just be n minus 1 divided by s. And then we're going to be having in minus 2. So this is what we have. This is what we have. Okay. Now we can go ahead again to find in minus 2. Yep, we can go again to find in minus 2. But let's just find it for the last time. Let's find in minus 2. So to find in minus 2 is this whole integral here. So this is the integral from 0 to infinity. It's just like we're trying to find reduction formula per se, or doing some iterative processes. So then we have t to the n minus 2 e to minus st dt. I believe by now you must have noticed the pattern. You must have noticed the pattern. So my u in this case will become t to the n minus 2. My dv will become e to negative st dt. So du will become, in this case, n minus 2 brackets t to the n minus 3. Because when you reduce minus 2 by 1, that means you've removed minus 3. So that will be dt. And then v in this case will still remain the same, e to negative st over negative x. Or negative s, sorry. So I'm going to use this very formula to do that. So this will become uv, so that's u and v together. So that will be t to the n minus 2, e to negative st divided by minus s. This is still going to be with the limit, minus integral, the integral v du. But I like putting du first. So this will be n minus 2, t to n minus 3, and then I want to put v next, e to negative st dt, the dt should be last, divided by negative s. Again, this is 0. This is going to be 0. So equal to, now for this part, my 0 to infinity. Now, these two negatives will give a positive. And then the n minus 2 divided by s is a constant, because this is with respect to t. They don't have t, so they are constant. So this will be n minus 2 divided by s, integral from 0 to infinity. Then we have t to the n minus 3 e to negative st dt. At this point, you notice that there's a pattern to this, because this will now become n minus 2 over s. Then we have in minus 3. Because again, it looks similar to this. The only difference is the n here is now n minus 3. So you then call it in minus 3. So it's similar. Now, let's collate everything we've been doing. Let's bring everything together. Remember that this is what in is. So in the first case, in was equal, this was the first case. So in was equal n over s, in minus 1. Then this is n over s. What was my in minus 1? Now, in minus 1 gave me this very answer. This is in minus 1. So this was my in minus 1. So I'm going to put the answer here. So this is times n minus 1 over s. Then I have in minus 2. Now next, what is my in minus 2? So we have n over s times n minus 1 over s times in minus 2. What did we get for in minus 2? This is what we had for in minus 2. So for in minus 2, this will become n minus 2 over s in minus 3. That is what we're going to be having, in minus 3. But then, again, this in minus 3, we didn't find it. But you can tell what it's going to be, right? You can tell. Because this is not looking as if we have n over s times n minus 1 over s times n minus 2 over s. That means this is actually going to become n minus 3 over s, then in minus 4. You see, it's going to follow up that very pattern. So there's actually a pattern to this. So this will become n over s times n minus 1 over s times n minus 2 over s times n minus 3 over s times, this will go on until, of course, we now have I to the 0. Because of course, when you get to 0, you have to stop. Because when you get to 0, that means you have t to the power of 0, which is 1. So what do you think I naught is going to become? So I'm going to come back to this, in. I think I need another color for this. Hold on. Yep. So I said we're going to come back to this. So let me just mark it here. Okay. So I'm going to come back to that. But first, let's find what I naught is going to be. Now, ideally, in is equal integral from 0 to infinity 2 to t to the n e to negative st dt. So this will be I0. That means n is now 0. So this will be integral from 0 to infinity t to the power of 0 e to negative st dt. Now this will become integral from 0 to infinity of 1 e to the negative st dt. Please, I don't want us to waste some time. But what does this look like? This looks as if I am finding the Laplace transform of a constant. That's what it looks like. So if you go back to like the second video on this playlist, you will notice that this looks like the integral of a constant. And the constant here is what? 1. So the answer of this will just be 1 over s. If you've been following, it's just going to be 1 over s. I don't want to waste time. I don't want to start, putting all of my limits. It's still going to be giving me 1 over what? S. So now let me plug this into this expression. Let me plug it into that expression. Don't know what's wrong with this board. It's always difficult to wipe off. Please remember to hit the subscribe button and like this very video. So we have in equal n over s times n minus 1 over s times n minus 2 over s times n minus 3 over s times, that's how it keeps on going until you end at I naught. And I naught is just 1 over s. Now, what does this tell you? There's a pattern to this. There's a pattern to this. So in will become, look at the numerator. You have n minus 1, n minus 2, n minus 3. This looks like something that I know in factorial. Because whenever you're dealing with factorial, you keep on multiplying with 1 less than the number until you get to 1. So this is actually a factorial. So this is n factorial. Because n factorial is n times n minus 1 times n minus 2 times, yes, that is what n factorial is. Then for my s, if you notice, there's as many numbers as n. Let me say what that means. If it's just 1, let me say we just have t to the power of 1. We're going to end here. So the value of s, the power of s here is 1. But this is 1, 2, 3, 4. What this is telling me is I am having almost the same number as what the value of n would be. Let me explain better. Let's come back. Where should I come back to? Okay. Let's come back to this very portion. Let's come back to this very one. Imagine if this is what in is equal to, or I even use a tinier one to explain, but this is what in is equal to. Now imagine if n is 3, for example. Imagine if n is 3, for example. This means we'll end here, right? Because 3 minus 3 will give us what? 0. Now, how many s do you think we're going to be getting? When n is 3, we're logically going to be having 4s. 4s. Now, why is it 4s? This is 1, 2, 3. But if this is now 3 minus 3, that's I0. And remember that I0 is 1 over s. Sorry. Remember that I0 is what? 1 over s. So somebody can say that there is actually s to the power of n plus 1. Because whatever your number is, whatever your n is, you are going to get as many numbers as that. And because there's going to be an extra s at the end, you can see from this, there's an extra s at the end. That s will then make up n plus 1. The plus 1 here is showing us that there's an extra s at the ending. That is why this formula would stand. And with this, you found the Laplace transform of t to the n. And this will become n factorial divided by s to the n plus 1. So this will be the Laplace transform of t to the power of n. So remember I said something, I think there's another way to solve this. I'm going to use gamma function to find this very transform again, because this looks like the gamma function. It's exactly the gamma function. So I can use it to solve that. So let's look at some examples. So the first one, the Laplace transform of t to the power of 3. So this will then become 3 I'm following this because my n is here. So I'm going to be saying this is 3 factorial divided by s to the power of 3 plus 1. So 3 factorial, that's going to be 3 times 2 times 1 divided by s 4. So this will be giving me 6 divided by s 4. Now, do you know that even if you come use this very formula here, you are still going to be getting the same answer as 6 over s4. Because now, when you put your 3, this will be 3 over s. This will be 3 minus 1 is 2. So 2 over s. Then this will be 1 over s. Then you remember, there will be an extra s. Because normally, if there was no extra, this would just be s cubed. Because I have 1, 2, 3. Just s cubed. Which matches the number of n here. Because n is 3. It matches the number of what? N. But then, it's not going to match the number of n unless I add an extra 1 to it. So that's why it's not going to be the same. All right. Another example. Let me wrap this up. I don't want to make this very, very long. It's becoming so long. Let's say we have the Laplace transform of 3t to the power of 3. To the power of 2. Now, in this case, this will be 3 times 2 factorial because my value of n here is equal to 2. So this will be 2 factorial divided by s to the power of 2 plus 1. So this will be 3 times 2 factorial is just 2 times 1. Then divided by s cubed. So this will be 6 over s cubed. And with this, we've completed this very chapter, this very part of it. So let's look at much more examples, things that are still very much important in Laplace transforms before we start applying it, because there is a vast number of applications for Laplace transforms. I'll see you in the next video. Remember to hit the subscribe button, like this video, and share it across to your friends and classmates. Bye.